All right, with this video, I want to go over some background into what Weibull Analysis is and what it gives us. And there'll also be a companion video to this explaining how to do it on a real sample set. So let's first get into some of the background. So as you are probably aware of our materials by now, these are ceramics, these glass rods, and they have a very inconsistent nature, and that's due to the flaws and irregularities within the glass. And so we tend to get variability in the fracture strength. And in this case, we're talking about the 4-point flexural strength. And so you can kind of just see it here. All these dots are various flexural strengths as a function of density. So that's one way that it can vary, but also just flaws and so forth. So because of this sort of inconsistent nature, traditional statistics don't work very well. So what we do to characterize this is, instead of being able to test just a few samples, we need a rather large sample to be taken, and then we're going to use a specific statistical approach to analyze them. And so basically what this approach will do is it will allow us to say, at a given stress value, what is a random sample's chance of survival. And so we'll talk more about this plot in a bit, but basically this S is the survival probability, so the higher the better, and then the lower the less likely to survive. And then so that's on the y-axis, and then on the x-axis, this is a measure of the strength. So the sigma is strength. And so this plot gives us that. So picking some survival probability, we can look and see what its strength value is for that. And so that will give us a probability of whether something will survive or not. So this probability of survival, in our textbook, we call this S. So this is the probability, the chance that it will survive a given stress level. So this is a function of stress, which is going to be the big one that we look at, but it's also a function of the volume or area under that stress. And so this is a classic experiment where the strength of glass fibers was taken. And so basically this is the tensile strength. So a tensile test of the fibers was done as a function of the fiber diameter. And what we see is when the diameter is very large, the strength is relatively low, but as we decrease the diameter, then the strength goes up, right? This is the whole principle of fiber woven composites, is that the strength goes up as the diameter goes down. And so this is a function of the volume under stress. And so for ceramics that are brittle in nature and are very inconsistent, there's a volume dependence of the strength, and that's due to a given volume having flaws in it. And so this is the probability of survival, so just a different term for it, but it's a function of the volume and also the function of the stress. So again, the strength will go up with the smaller volume being tested. So what we're going to use is we're going to use a Weibull distribution, right? So we typically think in Gaussian distributions when we talk about averages and standard deviations, but a Weibull distribution is different, because instead here, this is a type of approach we often call the weakest link approach. And this is very good for something with flaws, because a ceramic with a given set of flaws will break at the so-called weakest link, so the biggest flaw, the most detrimental to its survival, right? The other flaws don't matter. It's only that weakest link that actually matters. And so the Weibull distribution is great for this type of distribution, where the weakest link among a set is what causes it to fail. So this is obviously used in other fields as well, but brittle materials, looking at their profiles, such as strength, is one of the big reasons we use it. So what is it? So this distribution, Weibull distribution, is what we call a two-parameter semi-empirical distribution. So there's two parameters, and so if we want to look at the frequency distribution, we need to know what's called a shape factor. So you can kind of see with different values here, you see the shape is changing. This is also what's known as the Weibull modulus. So this determines the shape of the distribution, how wide or how narrow the curve is. And then we also have a random variable, x. So this is kind of the generic frequency distribution. So when we apply it for ceramic strengths, what we do is replace that random variable x with a normalized stress, because we need it to be unitless. So we normalize it by a normalizing factor. So this is the general equation for it, where sigma is ceramic strength. In our case, we're going to be interested in flexural strength. So this is the random variable, the stress level, and then there's also a sigma pi, which refers to a threshold. So this is basically the threshold stress below which the probability of survival is equal to 0. And then the normalizing parameter here at the bottom. And so this is known as a characteristic stress value, and it's taken at a specific survival probability. So just like the average is taken at a certain value, this is at a certain value, and the survival probability is 1 over E. So this is a given survival probability, the stress value will be this, and so this is our characteristic stress. For our experiments, we ignore this because we take the threshold as 0. So essentially, we're saying that there's always some stress where that is 0. So we basically just cancel this term out, and it becomes stress over the characteristic stress, and that's what we have as x. So therefore, our survival probability is, again, the fraction of samples that will survive a given stress level. And so we can write it here as an integral, or we can just kind of simply write it here, the solution, as the survivability probability is equal to the exponential of minus that random variable, which is stress over normalizing stress characteristic, raised to the Weibull modulus. So this kind of gives you in this case it's failure, but you can take in the reverse and look at success, and you see that how the applied stress varies. And so here we're basically taking this as something close to 0. So, so this is basically our function. This relates our two variables, the characteristic stress and the Weibull modulus, the two factors in our distribution, to the survival probability. And so we're going to see a version of this later. So for experimental data, we need to be able to approximate what the survival probability is. And so what we do is, for samples that are ordered in increasing strength, so we would start with the first sample, which is the weakest, and moving on up to the last sample, which would be the total number of samples. So for example, we have 30 or 100. We're basically counting up. We can calculate the survival probability of a given sample, the jth sample, by using this equation, and this will give us the survival probability for that given sample. So we need to know what sample it is and the total number, and then we can plug it in to this equation. All right, so here's the rearrangement of that expression that we saw before. And the idea was to linearize it. We've made a linear relationship so that we can determine our parameters. Because here, this m is the Weibull modulus. We can determine that from the slope because we've linearized this, so this is y mx plus b, right? So the slope is equal to negative the modulus. And we can also determine from the y-intercept here what the value of the characteristic strength is. So essentially, when we set this up for experimental data, we will be able to plot our data in this linear fashion and extrapolate our two parameters for the frequency distribution, because that's the two parameters that tell us information about the data set. So I want to take a brief second to show you the form of our Weibull distribution where the survival probability is equal to the exponential of the normalized stress value raised to the m power. Because I want to show you how we get that linear relationship. So how we basically start with this and get that linear relationship that you see. Because I think if you look at it, it has a very odd look, but it's for a reason. So let's kind of go through the steps and how we get this to a linearized form where we can solve for m and the characteristic strength sigma naught. Okay. So the first thing that we're going to do is there's a negative in here. So I can get rid of that by using the negative exponential rule. And so if I take 1 over the positive of that form that you see, that is the same as what we have up here. And so that's going to still be equal to s. So if I rearrange this, and bring this over to this side and the s over to this side, I get 1 over s equals exponential of sigma over sigma naught. And then that's, again, we've just gotten rid of the negative sign. So this is a plus. Okay? So first step. Now, if we want to make it linear, we're going to get rid of the exponential form. So to get rid of an exponential, I take the natural log. So I take the natural log of both sides, and I get natural log of 1 over s equals sigma over sigma naught raised to the m power, right? So now this is a function of something to the m power, the Weibull modulus, and so I need to get rid of this somehow. And the way we can do this is if it's a natural log or a log, I can bring this out front. So I'm going to take the natural log again, and if I do it here, I have to do it over here, right? So natural log 1 over s, and that's going to be natural log of sigma over sigma naught raised to the m power, right? And now I can move this m out front to multiply it. And so this is still equal to the same thing, and I've got m natural log sigma over sigma naught. So this is basically more or less the linearized version, but we're just going to do a couple things to simplify it. So I'm going to expand this out, m natural log sigma, and then these are divided so I can subtract them. So this is m natural log sigma naught, right? So just using the log rules, we can do that as well. Take the subtraction of something that's divided, and I still have this. And so at this point, this is a constant. This is our variable, and then this is our other variable. And we're going to do one last thing. We're going to take the negative of both sides. So technically speaking, this part isn't necessary, but it makes it more convenient for graphing. So essentially, if we take the negative of both sides, we get this. And in doing this, we have our linearized form, which is what you see in the slides. And so the important kind of thing, again, it's this negative natural log of 1 over s, which looks weird. So you plot that, and then you have negative m natural log sigma, and then plus m natural log sigma naught. So it looks complicated, but again, this is a linear form. This is effectively equal to our y, and then this. So this is basically our y, and then this is our slope. And so you typically call the slope m in that y equals mx plus b. So this is our x plus, and then this is our y-intercept, so b, right? So this effectively becomes x. This is our y. This is the slope. And then this is the y-intercept, right? So if we plot this versus this, that's the linearized form. And so the slope is going to be related to the Weibull modulus, and the y-intercept is going to be related to sigma naught, which we're interested in. And so using those factors, that's why we're linearizing this. So we can plot it, do a linear regression, find out the slope and the y-intercept, and determine the Weibull variables, which are Weibull modulus plus the characteristic strength. So that's how we kind of get from here to here, and why it's useful and why you want to do this. All right, for a second, let's look at the error involved in calculating the modulus, or m. So we see that the error depends on the number of samples tested. So the error decreases with more samples tested. And so this gets us into the classic paradox for our experiments is if we only do, for example, 10 samples, we have a really high error of about 40% the value of m. And if we go up to 30, we can get to 20%. But we have to go over 60 to get into the 90% confidence interval. And so this is the classic paradox of how much time do you have to run these samples compared to what error are you comfortable with. And so that's something that we have to consider for our sample sets. So in the lab, we always set 30 as our minimum. And so this kind of gives you an error of the, or approximate error value in the calculated modulus. All right, so let's take a look and see if we can use this Weibull analysis to compare different ceramics. So again, this is our classic Weibull plot. It's that linearized version. And so this, and the x-axis is a measure of strength, the natural log of the strength. And then this Weibull function is a factor of the failure survivability probability. Survival or failure. So this one's given as failure. So here, up here, it's saying up here, it's very likely to fail, and then very low likelihood of failure. So this allows us to compare different data sets to each other. So for the AL203, you see that the slope is very shallow. And so this means that it breaks over a wide range of strengths. So in other words, this is a very unpredictable material, right? If it's breaking over a range of strengths. So the slope in our two-function distribution, the slope m, the Weibull modulus, tells us about how close together the data is. So this is a very low number m, and it tells us that the data is really spread out, as opposed to the one over here, the Al203 plus 25% of the silicon carbide whiskers. This is a very steep slope, so the number is going to be much higher, and the data that is not spread out over a large range. So it's more predictable in terms of the if you know one sample how the other strengths will be. So in general, a higher Weibull modulus, or M, or slope, is going to be greater consistency in the data. And then the other factor is the characteristic strength. And again, that was where this equals 0. So if we basically plot a line across here, we're able to compare characteristic strengths. And we see that this would be the highest value, this would be the second highest value, and then this would be the third. So this is kind of comparison of averages, right? So this has a higher strength in general at that given probability than this one, than does this one. So that's what the characteristic strength tells you. It's basically the equivalent to the average in a Gaussian distribution. And the same thing, here's another comparison, only for this one it's different processing methods, and you can see the same thing. The slope tells you how consistent the data is, and then the value where this is equal, where this is equal to 0, where this acts as the natural log of 1 over s is equal to 0, tells you a measure of the regular strength. So here they're giving you the characteristic strength of 101, 121, and 130. So it's a matter of consistency. So this one has the highest consistency, but this one has a stronger strength. So these are kind of the two factors that we're looking at, is what's more important, predictability, in which this case the Weibull modulus would be more important, or is overall strength important, and less consistency is fine, then this one would be okay, right? So that's the information that you can get from this Weibull modulus.